Okay, so in the last class, we looked at conditions for a point being a local minimum, right? And some where we saw first and second order necessary conditions. In the case of convex functions, we saw that the first order necessary condition is also in some sense sufficient. So if you have an interior point within a constraint set and the derivative or the gradient happens to be equal to 0, then that point is guaranteed to be a local minimum. Not just a local minimum, it's a global minimum. All right. So that's something very useful. But all of the discussion that we did in the last couple of classes, it was mainly to determine whether a given point could be a local minimum or not. But it doesn't, given a set of constraints or given a particular function, how do we actually determine the minimum? How do we search for the minimum of that particular function subject to the constraints? That's the goal, right? The goal is to design efficient algorithms that will allow us to search for the minimum or at least some point close to the minimum. Okay. So towards that, we'll first look at algorithms for unconstrained minimization. Given some function, we'll assume that there's only one global minimum, and subject to these constraints, subject to these properties, we'll see how we can possibly search for a point that is close to the minimum of the function. So one reasonable assumption to make is, of course, let's start with functions over R, and slowly we'll use this to build algorithms for functions that are defined over Rn. All right. So the assumption that one assumption to make could be that f is a convex function, and the other assumption that we'll require is that we have some sense of where the minimum lies. If the minimum can be any point in Rn, then you can't really guarantee how long it would take for you to find the minimum. So we'll first assume that we have a coarse estimate of where this function could lie. All right. And the goal could be either following. So we want to design some kind of an algorithm such that, of course, finding the exact minimum may not be possible, because after all, we are looking at numerical methods to find or approximate the minimum. So at best, we can hope to find a point that is close to the minimum. And the condition that we can pose is one of two. So we could either say that we want a point that is epsilon close to the minimizer, or we want to find some x such that the function value is very close to the minimum. Okay. Note that if there's no further assumption on the function itself, then these two conditions need not be even comparable. All right. But for the most part, at least for this particular class, we will look for some particular point that is epsilon close to the minimizer. So we'll declare that the algorithm is successful if after a certain period of time, whatever the running time of the algorithm is, I get an x such that x is epsilon close to x star. Okay, that's the objective. Okay, is the setup clear? So when we talk about algorithms for minimization, and when I talk about, say, running time or complexity of an algorithm, I have to be clear. What does it mean when I say complexity? What does the complexity include? What are we given about the optimization problem itself? All right. Without this, you can't really talk about running time. So we'll make some assumptions, which is typically standard. So how do we measure complexity? All right, so I want to design an algorithm. Suppose I come up with some kind of an algorithm that, given a function, gives me a point that is epsilon close to the minimum. All right. How do I measure the complexity of this particular algorithm? What are typical ways to do it? What is the most natural way of measuring complexity? Yeah? Good. So one way of measuring complexity is you measure the number of arithmetic operations that were required to minimize this particular function. Right, that's one way of measuring. So let's say that, so one simplistic assumption is that addition, all arithmetic operations, addition, multiplication, subtraction, division, each of them take some constant amount of time, let's say unit time. And the total number of arithmetic operations that are required to come up with a minimizer or something that is epsilon close to the minimizer, that could be taken as the measure of computational complexity. But there's a slight problem with this in that the complexity doesn't depend not just on the doesn't depend only on the algorithm itself. It also depends on the function that you're trying to minimize. Because if your function itself is complicated, in the sense that just evaluating f of x requires a lot of complexity, then that itself could be huge. All right. So just to analyze generic algorithms, a general class of algorithms, we'll make another simplification. All right, just so that we're not bogged down by the number of arithmetic operations that we want to compute. So another way of measuring the time complexity or the running time of a particular optimization algorithm is to assume that any evaluating the function at any given point takes unit time. Okay, so we're given a function and we'll assume that we have access to this black box. All right, so it's called an oracle based method. So we assume that there is some black box. All right. And this black box is such that if I give some point x as input, it outputs the value f of x. Okay, and one function evaluation takes unit time. Okay, so this is what is called a zeroth order oracle because it tells me the value of the function at any given point. So one function evaluation takes unit time. I can also say, so for certain functions for which the derivative is well defined, I could also think of a first order oracle where I can not just evaluate f of x, but I can also evaluate the gradient of f at the point x. Right? That's called a first order oracle. So I give a point x, I have this black box which evaluates the gradient at the point x. Okay, so that's a first order oracle, and I can go on. There could be a second order oracle, third order oracle, and so on, depending on what I have access to. So when I say an algorithm, I also have to specify whether it's the algorithm has access to a zeroth order oracle or a first order oracle or so on. So you can think of this, if you were to implement this using a program, then effectively I have access to a function such that I give a point as input, it outputs the value of the function at that given point. or the gradient at that particular point. Okay. So essentially the complexity of an algorithm could be measured by the number of oracle accesses that I have to make. All right. So that's how we'll measure the time complexity. So the running time could be measured by number of accesses. Yeah.
Sir, how is the first order derivative related to the complexity?
So irrespective of whether you call the zeroth order oracle or first order oracle, we'll assume that it takes unit time. So maybe you know what the function is and you hand calculated an expression for the gradient of the function. That's one way of saying that you have access to a first order oracle. Okay. The total complexity that is required to compute the function is not counted in a sense, where we are sort of throwing all of it under the rug. Irrespective of which point you want to evaluate the function at, we assume that it takes the same amount of time. Same holds true for the gradient. We assume that no matter what the value of x is, the total time required to compute gradient of f is the same. Okay. So effectively, computing f or computing gradient of f has this additional overhead that we are not counting here, because we assume that someone has already written a function to do these two things. Number of times you call this particular black box or number of times you call this particular oracle, that is the only time complexity that we require. This helps because it allows me to compare the performance of an algorithm on two different functions, on two different optimization problems. Otherwise, the complexity of minimization would also depend on how complex the function is, how complex f is. But now I have a way of measuring the running time of an algorithm independent of what f looks like or what gradient of f looks like. Okay, does that make sense? It's also independent of the dimensionality of the input space and so on. Okay, so we are all keeping that under the hood. But in reality, when you're actually implementing the optimization problem or the optimization algorithm, you have to take all of these into account, because the dimensionality of the input space could play a very, very big role in determining the complexity. Okay, but for now, when we talk about running time of an optimization algorithm, all of these are not considered. All right. So we'll start with some very basic search methods for minimizing functions on R. All right. So the first is this. There are a number of such algorithms, and I basically just want to give you a flavor of what kind of algorithms are present. This need not be the best possible algorithm, but we'll see what we can do. So the basic assumption that we have is the following. So we are given a function, okay, and we are told that the minimum lies within some interval a0 to b0. That's given to us. We somehow know this. And given this, we want to find some point x. So maybe this is the point of minimum. This is my x star. My goal is to eventually come up with some point x that is very close to x star, that is epsilon close to x star. Okay. So the basic idea behind many of these search algorithms is to, well, you originally had this search space, which is this interval from a0 to b0. You try to iteratively reduce the search space from a big interval a0 to b0. You next try to find a smaller interval a1 to b1 whose length is less than a0 to b0, and then find an a2 b2 which has even smaller size, and so on and so forth. Okay. So it's an iterative process, and as we'll see, most of the algorithms that we design are all going to be iterative in nature, and they'll have a very similar flavor. Okay, so this class of algorithms tries to reduce the search space. There could be other algorithms which behave in a slightly different way. Okay, all right. So in fact, for this particular class of algorithms, we'll relax the conditions on f even more. We don't even require f to be convex. We just assume that there is a unique minimum, and the function f has the following property. So over the interval from a0 to x star, that is everywhere to the left of the minimum, we'll assume that the function is decreasing. Okay, that's something that we'll require. F is and when I say decreasing, strictly decreasing. Okay. So f of x or whatever f of x1 is less than f of x2 for x1 greater than x2. Where x1 and x2 are points between a0 and the point of minimum. And similarly, over to the right of the minimum, I'll assume that the function is strictly increasing. So over x star comma b0, f is increasing. Okay, so the function could even look, for example, something like this. All right. So this is not something that is convex. Need not be convex, but just want it to be strictly decreasing to the left and strictly increasing to the right. All right. And we'll assume that we have access to only a 0th order oracle. So the function need not even be differentiable. Okay, so how I evaluate f is not important, but I can evaluate f of x for any point x between a0 and b0. All right. The setup is clear. Okay, any questions? Fine, let's say that we do the following. So I start with a0, b0. My next step, I'm going to pick some a1, b1. a1, b1 such that a0 obviously is less than a1 is less than b1 is less than b0. And maybe I ask for something more. At each step, I want to reduce my search space by at least some fraction. Okay, so let's say that I want whatever the reduction on one side. Let's say a1 minus a0. I can just assume that the reduction is symmetric on both sides. So this is equal to B0 minus B1. So the length of this particular interval is the same as the length of this particular interval. And this is some rho times B0 minus A0. Okay. The main idea behind this golden section search is the following. Now, I've essentially split this entire region into 3 subintervals. Right? One is this particular region, the other is this particular region, and the third is this particular region. At each step, I want to eliminate one of these intervals as a possibility. Okay? And I want to be able to do so only knowing maybe what is f of a1 and what is f of b1. All right? So let's look at possible conditions to understand why this is enough or what can happen. So suppose that f of a1 is less than or equal to f of b1. So this is what it looks like. So I have the point A0, B0, A1, B1. So as it so happened, f of A1 is less than or equal to f of B1, or let's say without loss, let's start with f of A1 strictly less than f of B1. So this is my f of A1, this is my f of B1. Okay. What can you say about f of A0? What should happen? So f of A0 should be greater than f of A1. Do you all agree? Because from A1 to B1, the function happened to decrease. Which one? Oh, I'm sorry. That's correct. Yeah. Okay, so this is how it is. Let's now see what can you say about f of B0. f of B0 should be greater than f of B1. Because otherwise, if f of B0 was less than f of B1, that can't happen because I've assumed that the function is monotone, that essentially there is only one point of minimum, all right, and the function has no maximum in a sense between A0 to B0. Okay, so this condition can never happen, and therefore f of B0 should be somewhere above f of B1. Okay, but what can you say about the minimum? Where do you think the minimum can lie? Can it lie between A1 and B1? Potentially yes, because the function could look something like this, right? It could be, say, something like this, right? It could also lie between A0 to A1. Do you agree? Because, for example, it could be something like this. Right? So the minimum can be anywhere. But can the minimum ever lie between B1 and B0? That is not possible. Right? The function can't increase and then decrease. That's something we've explicitly forbidden. We know that that doesn't happen with this particular function f. All right? So for sure we know that the minimum x star cannot lie between B1 and B0. All right, so I can eliminate this part and now focus only on this particular subinterval from A0 to B1. All right, and then I could keep repeating the process. All right, so iteratively I keep reducing my search space in this manner, and I end up with something that is close to the minimum. I know that at each stage I'm reducing the interval size by some amount. What is the amount that I'm reducing it by? What is the size of the interval is B1 minus A0, right, in this case. And what is the length of B1 minus A0? Yeah? Why 1 plus rho by 2? So what is the length of B0 minus B1? That's the amount that I've removed, right? Right. So the amount that I've removed is, so this is B0 minus A0 minus so I have B1 minus A0, which is my search space at the end of the first step. This is equal to B0 minus A0 minus B0 minus B1. But what is B0 minus A1? I'm sorry, B0 minus B1. It is rho times B0 minus A0, right? Because that's how I've chosen B0 minus. I've said that that's how I'm going to choose B1 and A1. So this is equal to 1 minus rho times B0 minus A0. So I've reduced my search space by a fraction 1 minus rho every single time. So similarly, I choose B2 A2 and B3 A3 and so on. I keep doing this until this finally I bring it down to a sufficiently small region. Okay, but now let me go a step further. All right, remember that the complexity is essentially the number of oracle accesses that I need to make. How many oracle accesses do I need to make in every step? 2, right? The way I've described it, I need to make 2 oracle accesses because I have to find A1 and B1, similarly A2, B2 and so on. Let's see if we can reduce the number of oracle accesses to just 1 per step, except the first step. All right. So what I'll do is, instead of choosing A2, B2 arbitrarily, I'll choose, so I want to reduce. Okay, so if I implement it naively, the number of per step, this is 2, right? Because I need to compute f of at and f of bt in time step t. But I'll do it in a slightly more clever fashion. So where I get 1 oracle access per step, I'll choose B2 to be equal to A2. Sorry. So suppose that this happened, that is, in the first time step, suppose I eliminated the interval from B1 to B0. All right. I'll choose my next B2 to be equal to A1. I'll choose this to be B2 and this to be A2, something there to be A2. Okay, so now at the next step, I only need to evaluate f of A2 because I already know what is f of B2. It's equal to f of A1, which I evaluated in the previous step. Right? Does that make sense? So let me explain it visually. There are two conditions. All right, I had my A0, B0, and I have my A1, B1, A1, B1. Suppose in the first step I eliminated B1 to B0. I'm going to choose this to be my B2 and something over here to be my A2, something to the left of it to be my A2. Suppose on the other hand, I eliminated this particular region, then I'm going to choose B1 to be my A2 and something here to be my B2. I can't do it all the time. I have to choose my row very carefully. Otherwise, I cannot do this. Okay, but this is something that by a clever selection of row, I can do this. And using this clever selection of row, I reduce the number of times I have to evaluate f. Right? Because in time step 2, I only have to evaluate f of B2 or f of A2. I don't need to, in this case, I don't need to evaluate f of B2, right? I don't need to evaluate this f of B2 in case 1, and I don't need to evaluate f of A2 in case 2. Is the principle clear? Okay, so for what values of row can I actually do this? So remember that, so this is possible only for a certain value of row, not for all values of row. So what are the conditions on row? So of course I want row to be less than half. That's a basic condition, just as a sanity check. And I want A1 minus A0 to be equal to B0 minus B1 equal to rho times B0 minus A0. And I also want, let's look at the first condition over here. So I want B2 to be equal to A1. All right. Okay, is that clear? Now, remember I want a reduction by a fraction rho in every step. Okay, so what can I say about the length of this interval from B2 to B1? What can I say about B2 minus B1 in terms of, say, B1 minus A1? Let's go step by step. Very basic.
Rho into B1 minus A1.
So B2 minus B1 should be equal to rho times B1 minus A1. Do you agree with this part? Because I basically want it at every step. Right? So at each step I want AT minus 1 to be equal to BT minus 1, and this should be equal to rho times BT minus 1 minus AT minus 1.
And also minus sign, right?
Sorry, which one?
Because we're doing B2 is less than B1.
B2, correct. That's right. So this should be B1 minus B2 should be equal to rho times B1 minus A1. All right. But I know that
What is it? B1 minus
I'm sorry, what? Why is it B1
A1.
minus?
B rho times B1 minus A1.
That's correct. You're absolutely right. The new interval was B1 minus A0. So it's rho times B1 minus A0. Good catch. Yes. Okay. So the overall interval was effectively A0 to B1. That's my search space, because I had effectively eliminated this particular region. That's the assumption. Right? So the search space is an interval of length B1 minus A0, and therefore I want B1 minus B2 to be equal to rho times B1 minus A0. Right? So let's try to evaluate this and express all of this in terms of B0 minus A0, so that I get some conditions that depend only on rho. So what is B1 minus B2 equal to?
1 minus 2 rho times B0 minus.
So B1 minus B2 is equal to B1 minus A1. B1 minus A1, which is equal to 1 minus 2 rho times B0 minus A0. What about the right hand side? What is rho times B1 minus A0?
Rho times 1 minus A.
It is rho times 1 minus rho times B0 minus A0. Is that okay? Okay, good. So then I can cancel this B0 minus A0 on both sides, and all I get is a simple equation. 1 minus 2 rho equal to rho into 1 minus rho. All right, which is rho minus rho square. So rho square minus rho plus 1 should be equal to 0. I'm sorry, rho square minus 3 rho so rho square minus 3 rho plus 1, this is equal to 0. What is rho equal to? Yep, so it's just 3 plus or minus square root 9 plus 1, 10, which is root 5 divided by 2. So it's 9 minus 4 whole divided by 2. Right? So this is the golden ratio. I'm sorry? Yeah. So 3 minus square root 5 by 2. Ultimately, we want a row that is less than half. So we choose rho to be equal to 3 minus root 5 divided by 2.
So this is 1 minus 1 by 5, 1 by what?
Sure. All right, so the main point here is that if we go back to this equation, 1 minus 2 rho equal to rho into 1 minus rho. This is the same as 1 minus 2 rho divided, or I can rearrange this to give the following. So I have 1 minus 2 rho equal to rho into 1 minus rho. Rho minus rho square. So let me take this. Okay. So I have rho square minus 3 rho plus 1. Or rho minus 1 the whole square equal to rho, right? Or 1 minus rho the whole square to be equal to rho. Or 1 minus rho to be equal to rho by 1 minus rho. So in the first step, right, this is the length of the region that remains, right? This is the length of, so have the residual search space or length of the residual search space divided by length of the original search space. This is equal to, in the next step, the length of this is the length of sort of the shorter segment, that is the region that was removed, divided by the length of the region that remains. So that's another way of just looking at the golden ratio. 1 by 1 plus? Yes. So effectively all we get is rho equal to 3 minus root 5 by 2. Right? So that's the optimal choice of rho that gives me this particular condition, that B2, I can, at every stage I can choose BT plus 1 to be equal to AT. All right. Any questions?
Mars step lookups.
Correct.
But have you also reduced or increased the speed of convergence? Finally, that's what is going to happen.
Potentially yes, but this is just a rule, right? Again, I'm not saying that this is the best possible rule that minimizes the time that is required to reach the minimum. Okay. My goal was to fix a particular choice of rho. In particular, rho remains fixed throughout. I don't change rho in every iteration. I could also look at different classes of algorithms where I change the rho in every step, which could potentially lead to faster convergence. But what I want is that at every step, I just make one oracle axis. All right. So what is the speed of convergence? So if I want to get to within epsilon of, I want, let's say xt minus x star to be less than some particular epsilon, or maybe what I want to say is that after a certain number of steps, my search space is bt minus at. Suppose that this is less than epsilon, which guarantees that I have an x which is epsilon close to x star. How many steps would I require? What is bt minus at in terms of b0 minus a0? Correct. So this is nothing but 1 minus rho whole to the power t times b0 minus a0. A0 should be less than epsilon, or sort of if you rearrange, you get epsilon divided by b0 minus a0 to be less than, greater than, let me sort of rearrange, 1 by 1 minus rho whole to the power t should be greater than b0 minus a0 divided by epsilon, or t should be greater than log b0 minus a0 by epsilon, right? Right. So in a sense, if you, again, rho is something that is a constant, and epsilon is really the epsilon, what b0 minus a0 and epsilon are really the parameters which can change, right? Which essentially determine how long it takes for convergence. And so here what we observe is that the overall time that is required, the number of oracle axes that you need to make, essentially grows as log of b0 minus a0 divided by epsilon. Right? Another way of looking at it is, so if I look at 1 minus rho, so the effective reduction in the search space is 1 minus rho in each step. And if you sort of compute it, then 1 minus rho happens to be is approximately 0.618. So at each step, the new search space is roughly 0.618 times the search space in the previous iteration. Right? Any questions? Question?
So why can't you take rho to be close to half, which would decrease the thing?
But then I will not have that property. If I choose any other value of rho, I'll have to make 2 oracle accesses in each step.
How do you check which is faster?
Which one?
If you take rho close to 2 and have 2, or rho close to half and have 2 or
So then you can count the number of oracle accesses, right? You'll see that it's not enough. The total number of oracle accesses that you'll need to make would be more. Of course, all of this is assuming that you fix a particular row. All right? You can choose row to be arbitrarily close to half. Let's say 0.55. But then you would increase the number of oracle accesses by like a factor of 2. All right? Okay, so let's perhaps look at a quick visualization of what this looks like. All right, so suppose I started out with this particular function, which is just sin x from pi by 2 to, I don't know, something that's a little over 2 pi. Okay. And I'm using this particular root. So I start with a0, b0. a1 and b1 are marked in green. Okay. So that's a1, b1. Now I get a2, b2. Okay. I can keep repeating this a3, b3. So let me perhaps just go back. Right. So out of these two, which region should be eliminated? The leftmost, that is from a0 to a1. Right? The minimum obviously lies in the interval from a1 to b0. And that's indeed what the algorithm does. Right? So at step 2, you only retain the region from between the two red dots. That's my a1 and b1. And my a2 and b2 are going to be the two green dots. Next step, what should happen? You should eliminate the rightmost part, and that's also because f of a2 is less than f of b2. Right? And the same process continues. right? So iteratively you keep reducing the search space until you get to a certain point. Say, 9. Right, so you get closer and closer to the minimum. So, but then as we saw, as you suggested, we could try to reduce the search space at every step. Instead of reducing the search space by a factor of 0.61, can we get something where we reduce the search space by a factor close to half? If yes, that would be great. We can do so if we have some extra information. That is, we have access to not just a 0th order oracle, but also a 1st order oracle. All right, and again, it's fairly natural to do so. So again, we'll have the same assumption as before. That is, f is decreasing to the left and increasing to the right. That's the only assumption that we require. And we have access to, say, in fact, we don't even need access to a 0th order oracle. Just one access to 1st order oracle is fine. So I have some function over here, and my search space is A0 to B0. What I'll do at every step is fairly simple. Maybe I should have, I'll take the midpoint between A0 and B0. Okay. Maybe this is my F. I'll take the midpoint between A0 and B0 and just check what is the slope of the function at that point. I evaluate the derivative. If you are to the left of the minimum, then what should happen? Derivative should be negative. If you are to the right of the minimum, what should happen? Derivative should be positive. So just using this, you can eliminate either the interval to the left or the interval to the right. Right. So now, in this case, this region is eliminated because the derivative is negative. So you know that the minimum has to lie on the right. And you keep repeating the same thing. You take another point, the midpoint of this new interval that I have, and again evaluate the derivative at this particular point. I see that the derivative is positive, so the minimum should lie to the left. So I can now eliminate this particular region and repeat. Take the point, maybe the derivative is, maybe perhaps this is the point of minimum. So I can eliminate this region, and so on and so forth. You keep doing this. All right. Again, we for this we do require this condition that f is strictly decreasing and f is strictly increasing. All right. I can't have the slope to be 0 at any other point. That's a requirement. All right. Any questions? So now, at what rate is my search space decreasing? Half, right? So again, if I want bt minus at to be equal to be whatever less than epsilon, my bt minus at is 0.5 to the power t times b0 minus a0. All right, and this should be less than epsilon. So effectively I get the same as I had earlier. Right. So earlier I had t to be greater than log b0 minus a0 by epsilon divided by log of 1 by 1 minus rho. Now effectively it just becomes t should be greater than log b0 minus a0 divided by epsilon divided by log 2. So the total time that is required to get epsilon close to the minimum is now decreased by a constant factor. The dependence on epsilon and a0 minus b0 that still remains the same. That hasn't changed. But this constant at the bottom, that is improved. Particularly for large t, this can make a significant difference. All right, and here is just a simple sort of visual illustration of how that works. Again, for the same function that we had, you take the midpoint, take the midpoint, take the midpoint, see whether you have to go look to the left or to the right, and keep repeating this. All right. Any questions? All right. So these were sort of two simple approaches, and both of these required you to know at least to start with some interval a0 b0. All right. In practice, how do you get this? Like, who tells you what a0 and b0 are? It's not easy. All right. But in many cases, you can get a particular a0 and b0 in the following way. So finding a0 b0, effectively, if you think about it, to find an a0 and b0, it's enough to search for suppose I'm able to find some three numbers a, b and c such that a is less than c is less than b, and f of c is less than f of a, and f of c is less than f of b, which means that I have some a right. Somehow I'm able to find an a, b, and some C anywhere in between A and B, such that if I evaluate at these 3 points, f of C is strictly below f of A and f of B. Then you're kind of guaranteed, again I'm assuming that to the left of x star the function is decreasing, to the right of x star function is increasing. So this implies that there is a valley in between A and B, and therefore the minimum should lie between A and B. So then you can take your A as A0, B as B0, and then proceed. That's one particular approach. All right. So this whole sort of first step of searching for an appropriate A0 and B0, this is called bracketing. And typically we will assume that, like when we use these kind of search algorithms, we will assume that we've already done this sort of bracketing. Somebody has already told us A0 and B0. In fact, for analyzing many optimization algorithms, we'll assume that someone gives you an approximate search space, some bounded region where you know that the minimum exists. All right. Any questions? Okay. So it's a good time for a quiz. No more than 3 in a bench. Does everybody have a sheet? Find all feasible directions